Namaskar. Today I will discuss the examples on Hamilton principle. Use Hamilton principle to find the equations of motions of a simple pendulum. In case of simple pendulum, the only generalized coordinate is theta and Lagrangian is given L is equal to 1 by 2 ml square theta dot square minus mgl into 1 minus cos theta. The Hamilton's principle states that the path followed by the pendulum is one along with the line integral of the Lagrangian is extrema. That is delta T0 to T1 L dt is equal to 0. Integral from T0 to T1 delta 1 by 2 ml square theta dot square minus mgl 1 minus cos theta dt is equal to 0. Integral from T0 to T1 ml square theta dot delta theta dot minus mgl sin theta delta theta dot dt is equal to 0. Since delta theta dot of d by dt is equal to d by dt of theta dot, therefore integral from T0 to T1 ml square theta dot d by dt of delta theta minus d by mgl sin theta delta theta dot dt is equal to 0. Integrating the first integral by parts, therefore ml square theta dot delta theta from T0 to T1 minus integral from T0 to T1 ml square theta dot plus gl cos sin theta delta theta dt is equal to 0. Since delta theta from T0 to T1 is equal to 0, we have therefore integral from T0 to T1 ml square theta double dot plus gl sin theta delta theta dt is equal to 0. Since delta theta is arbitrary, we have theta double dot plus gl sin theta is equal to 0. Therefore, theta double dot plus g by l sin theta is equal to 0. This is required equations of motions of the simple pendulum. Spherical pendulum. A particle of mass m is moving on the surface of the sphere of radius r in the gravitational field. Use Hamilton principle to show the equations of motion is given by theta double dot minus p phi square theta cos theta divided by m square r square sin square theta minus g by r sin theta is equal to 0, where p pi is the constant of angular momentum. Proof. Solutions. Let a particle of mass m be moving on the surface of the sphere of radius r. Then particle has 2 degrees of freedoms and 2 generalized coordinates theta and phi. Therefore, the Lagrangians of the system is given by L is equal to 1 by 2 mr square theta dot square plus sin square theta phi dot square minus mgr cos theta. The Hamilton principle states that the path followed by this particle between two time interval T0 to T1 is one along with the line integral of the Lagrangian is extrema. That is delta T0 to T1 L dt is equal to 0. That is integral from T0 to T1 delta 1 by 2 m r square theta dot square plus sin square theta phi dot square minus mgr cos theta dt is equal to 0. Integral from t0 to t1 mr square theta dot delta theta dot plus sin square theta phi dot delta phi dot plus sin theta cos theta phi dot square delta theta plus mgr sin theta delta theta dt is equal to 0. Since we have d by d of delta of d theta by dt is equal to d by dt of delta theta, therefore integral from t0 to t1 mr square theta dot d by dt of delta theta minus sin square theta phi dot d by dt of delta phi plus mr square sin theta cos theta phi dot square plus mgr sin theta delta theta dt is equal to 0. Integrating the first two integral by parts, we get, and so on. We have therefore integral from t0 to t1 mr square theta double dot minus sin theta cos theta phi dot square minus g by r sin theta delta theta dt plus integral from t0 to t1 mr square d by dt of sin square theta pi dot delta pi dt is equal to 0. Since theta and phi are independent and arbitrary, hence we have theta double dot minus sin theta cos theta pi dot square minus g by r sin theta is equal to 0. mr square d by dt of sin square theta pi dot is equal to 0, that is mr square sin square theta phi dot is equal to p pi constant. Then eliminating phi dot between, we obtain theta double dot minus p phi square cos theta divided by m square r raised to 4 sin square theta minus g by r sin theta is equal to 0 as the required differential equations of motions for the spherical pendulum. Hamiltonian formulations. We have developed Lagrangian formulations as a descriptions of mechanics in terms of the generalized coordinates and the generalized velocity with time t as a parameter in and the equations of motions were used to solve some problems. We now introduce another powerful formulations in which the independent variable are the generalized coordinate and the generalized coordinate momentum known as Hamilton formulations. These formulations is an alternative to the Lagrangian formulation but proved to be more convenient and useful, particularly in dealing with the problems of modern physics. Hamilton function, the quantity summation of pj qj dot minus l, where when expressed in terms of the q1 q2 dot qn p1 p2 dot pnt is called the Hamiltonian and it is denoted by h. H is equal to h of qj pjt is equal to summation of pj qj dot minus l. Hamilton's canonical equations of motions define Hamilton's and hence derive the Hamilton's canonical equations of motion. We know the Hamiltonian h is defined by as h is equal to h of qj pjt is equal to summation of pj qj dot minus l. Consider h is equal to h of qj pjt, where we find from equation 2 that dH is equal to summation of dou H by dou Pj dPj plus summation of dou H by dou Qj dQj plus dou H by dou T dt. Now consider H is equal to summation of Pj Qj dot minus here. Similarly, we find dH is equal to summation of Qj dot dPj plus summation of dQj dot Pj minus dL. dH is equal to summation of Qj dot dPj plus summation of dQj dot Pj minus summation of dou L by dou Qj dQj minus summation of dou L by dou Qj dot dQj dot minus dou L by dou T dt. We know the generalized momentum is defined as Pj is equal to dou L by dou Qj dot. Hence, equation 4 reduces to dH is equal to summation of Qj dot dPj minus summation of dou L by dou Qj dQj minus dou L by dou T dt. Now, comparing the coefficient of dPj, dQj and dt. In equation 3 and 5 we get Qj dot is equal to dou H by dou Pj, dou by L by dou by Qj dot is equal to minus dou by H by dou by Qj, dou L by dou T is equal to minus dou L by dou H by dou Pt. However, from the Lagrange's equations of motions, we have Pj dot is equal to dou by L by dou by Qj. Hence, equation 6 reduces to Qj dot is equal to dou H by dou Pj and Pj dot is equal to minus dou H by dou Qj. There are the required canonical equations of motion.